Albert in Wonderland. Einstein and Lorentz, avid tennis players, play a fast-paced game on a court where they stand L equals 20 meters from each other. They play without a net. The tennis ball has mass m equals 0.058 kilograms. Ignore gravity and assume that the ball travels parallel to the ground as it travels between the two players. Unless otherwise specified, all measurements are made by the two men. Part A. Lorentz serves the ball at V0 equals 80 meters per second. What is the ball's kinetic energy? Alright, so Lorentz serves the ball at 80 meters per second. The ball travels parallel to the ground towards Albert. What is its kinetic energy? Now, this speed, V0, which is 80 meters per second, is obviously much less than the speed of light, which is 3 times 10 to 8 meters per second. Therefore, we can say that this is non-relativistic. If it is non-relativistic, the kinetic energy is given by 1 over 2 mass of the ball, its speed squared. And we know the mass of the ball is 0.0580 kilograms. We can plug that in for kinetic energy. So we have 1 over 2 0.058 times 80, its speed squared, and that gives us a kinetic energy of 186 joules. Okay, let's move on to part B of the problem. Einstein slams a return at V1 equals 1.8 10 to 8 meters per second. What is the ball's kinetic energy? Well, this time the speed of the ball is comparable to the speed of light in vacuum. So 1.80 times 10 to 8 meters per second is less than but comparable to the speed of light. Therefore, this is the relativistic situation. So the relativistic kinetic energy is given by gamma minus 1 mass speed of light squared. The relativistic correction factor gamma is 1 over square root of 1 minus V1 squared over C squared. This is all inside the square root. Okay, so we can calculate the relativistic kinetic energy as the relativistic correction factor 1 over 1 minus V1 squared over C squared inside the square root minus 1, so that's gamma minus 1, m c squared. Now all we have to do is plug in the numbers for the relativistic kinetic energy. So K sub r is equal to 1 minus, what is V1? 1.8 10 to 8. So 1.8 squared divided by 9, it's 3 times 10 to 8. So they have the same 10 to 8 power. So we have 1.8 squared divided by 9. And this is to the power minus 1/2. So this is our gamma. Minus 1 multiplied by the mass of the ball, 0.058, and the speed squared, 3 times 10 to 8 squared. And this gives us, for the relativistic kinetic energy, 1.30 times 10 to 15 joules. So that's the answer to part B. Let's look at part C. During Einstein's return of the ball in part A, a white rabbit runs beside the court in the direction from Einstein to Lorentz. The rabbit has a speed of v rabbit 2.2 10 to 8 meters per second relative to the two men. What is the speed of the rabbit relative to the ball? Okay, so we have the S reference frame, which is the reference frame of Einstein and Lorentz. That's the stationary reference frame. We have the reference frame of the ball that is moving with speed v1, because it was after during Einstein's return of the ball, which means it's the relativistic one. And this S prime reference frame is moving with respect to S reference frame with speed v1. And if they are locating the rabbit, the position vector of the rabbit according to S reference frame is r, according to the ball reference frame. So this is the ball reference frame, the S prime reference frame is r prime. If at t is equal to 0, these two reference frames overlapped, in time t, the origin has moved a distance v1 times t. So we can see that there is a relationship between these vectors. R vector, the position of the rabbit reported by the S reference frame, is v1t, the relative velocity of the ball with respect to the S frame times t, plus r prime, the position reported by the ball reference frame. And if I take a derivative, the velocity according to the S reference frame for the rabbit is v1 plus v prime. And why is that? Because the time is the same measured in two reference frames. So this tells us that v prime, the velocity reported by the ball reference frame, is the velocity reported by Einstein and Lorentz minus v1. So v prime is the velocity reported by the S reference frame, which is 2.2 10 to 8 meters per second, and the ball has 1.8 meters per second times 10 to 8 in I hat. So I see that the velocity reported by the primed reference frame is 0.4 times 10 to 8 I hat in meters per second. And what have I done here? I have used a Galilean transformation. So I have an answer using Galilean transformation. However, we know that in the relativistic situation, we cannot use the Galilean transformation. So let's do this properly using the Lorentz transformation. Now, for the position of the ball, it's only moving on the x-axis actually. So I can just say x, the position reported by Einstein and Lorentz, is v1 times t prime plus x prime times gamma. So this has been modified. Time is measured differently in the prime reference frame. So v1 t prime plus x prime times gamma, relativistic correction factor. And the way time transforms, t is equal to t prime plus x prime v1, the product of these two, divided by c square multiplied with gamma, the relativistic correction factor. And if I write this in differential form, dx is equal to v1 dt prime plus dx prime times gamma, and dt is equal to dt prime plus v1 dx prime divided by c square multiplied with gamma. And if I look at the velocity transformation, dx dt, this is taking this into d prime parentheses, and gammas will cancel for dx dt. So I will have v1 plus dx prime dt, which is v prime. So I will have, for this transformation, v1 plus v prime divided by 1 plus v1 v prime over c square. Okay, so the way I have achieved this, I've taken this into dt prime parentheses. I have 1 plus v1 v prime over c square times gamma, and v prime is dx prime dt prime. So let me note that here. V prime is dx prime dt prime, and v is, here this is v dx dt. Okay, so I have this so-called Lorentz transformation. This is Lorentz velocity transformation. Between these two reference frames. Now, if I have the unprimed quantities on the right and the primed quantities on the left, what happens is this sign changes. So I will have a minus sign introduced here and a minus sign introduced here. So for v prime, I'm going to have for the proper transformation, it's going to be, this is the speed, so it's absolute value of v1 minus v prime. And what was v prime? V prime is the velocity measured by the s prime reference frame, and v1 is the speed of the ball. Okay, so if I take v prime to the left hand side, this is going to become v, which is the speed measured by the s reference frame, and the speed of the rabbit measured by the s reference frame was 2.2 10 to 8 meters per second. So it's going to be velocity of the rabbit measured by the s reference frame, vr, minus v1 divided by 1 minus v1 vr over c square. So that's the proper transformation. And plugging in the numbers here, I obtain the speed of the rabbit measured by Lorentz and Einstein was 2.2. The speed of the ball measured by Lorentz and Einstein was 1.8, 10 to 8, divided by 1 minus 2.2 times 1.8 over 9, 10 to 8, 10 to 8 divided by 10 to 16, they cancel out. So that gives me, for the speed of the rabbit measured by the ball reference frame, to be 7.14 times 10 to 7 meters per second. Okay, so here I'm measuring the speed. So I don't consider the sign here. So this is just going to be absolute value. All right, so what have we done in this part? First, I tried to do the Galilean transformation to see what will happen. So if the rabbit is measured by the ball reference frame, I measure V prime. If the rabbit is measured by the S reference frame, for its velocity, I measure V, which I called V sub R. So this is what I call V. Okay, and the Galilean transformation tells me R, the position of the rabbit with respect to S frame origin, is R prime plus V1t. So basically I have these two vectors adding up. And if I take a derivative of this, I get V, the velocity measured by the S reference frame is V1, the velocity of the ball reference frame with respect to S reference frame, plus V prime, the velocity measured by the primed reference frame. So V prime is VR minus V1. Okay, so this is going to imply that 2.2 minus 1.8 10 to 8, 0.4 10 to 8 I had in meters per second. Now, if I use the proper Lorentz transformation, first of all, I note that all of this motion is on the x-axis. So what I'm calling r here is really the x. X is v1 t prime plus x prime multiplied by gamma. And t is not equal to t prime in Lorentz transformation. It is t prime plus x prime v1 over c squared multiplied with gamma. Writing this in differential form, dx is v1 dt prime plus dx prime gamma, and dt is dt prime plus v1 dx prime over c squared times gamma. And if I divide these two, dx and dt, noting that this is dt prime times 1 plus v1 dx prime dt prime, which is v prime over c squared gamma, I obtain v is equal to v1, it's going to be v1 plus v prime. So it's going to be v1 plus v prime because it's divided by dt prime divided by 1 plus v1 v prime over c squared. That's the Lorentz transformation. Now, if I do the primed version of this transformation for v prime, I would have instead of the Galilean transformation where I had v minus v1, now I have v minus v1, velocity of the rabbit is v, divided by 1 minus v1 v rabbit divided by c squared. Okay, so that's the proper Lorentz transformation. So instead of this, I have this divided by an relativistic correction here, 1 minus v1 vr over c squared. And the speed that I'm measuring here is going to be 2.2 minus 1.8 10 to 8 divided by 1 minus 2.2 1.8 over 9. And that gives me my final answer. The speed measured by the ball reference frame is 7.14 10 to 7 meters per second. So the speed of the rabbit relative to the ball is what I have just found. Now in part A, I had a non-relativistic kinetic energy, 1/2 mv0 square. In part B, I had Einstein sending the ball to Lorentz at a relativistic speed, so the kinetic energy was gamma minus 1 times mc square, and gamma is 1 over square root 1 minus v1 square over c square, where v1 is the speed with which Einstein slams the ball.